Right, tonight I want to talk about a paper by John O'Quigley, which contains some fascinating ideas, very interesting statistical analysis, but I think also contains a mistake, which is actually an interesting mistake because it has led me to some new insight into the roster chart. So his paper is about the roster chart. And the theme of his paper is that, well, we understand that this was constructed by a process of refinement and elimination based on a bigger data set. So here are 25 events, and John takes in this paper a number which he's I'm not quite sure exactly where it comes from, but we can take it by way of argument, of 61. Suppose there were originally 61 events, and that these little black diamonds are scattered all over it. And suppose that what happened was that the 61 was actually the pattern of what you would expect with 38. Here, 38 nurses. Here's nurse Lucy Letby, number 23. There were 38 innocent nurses, and this pattern was just random and went all the way down to row 61. And then it was found that there were exactly 25 events where Lucy was present, and the remaining 61 minus 25 she wasn't, and therefore those 61 minus 25 rows have been thrown away, and we get this extraordinary and for many people extremely sinister pattern, supposing to show that whenever something bad happens, Lucy Letby is always there. Well, in fact, she wasn't always there when something bad happened, because apparently there were a whole lot more shifts, and all of the shifts were mixed up together, all 61, and every shift where Lucy does not happen to be present, they have been deleted, which leaves these ones left over. And now we get the illusion that Lucy is connected to bad things happening. Now, I agree that it's an illusion, and there are several reasons why we know it is an illusion. And indeed, that idea that there was a much bigger list and it got refined and rows thrown away is now very clearly true. And this is especially been clearly nicely exhibited in a recent YouTube film by Peter Elston, who actually got further data from and information from Dowie Evans. It's really useful to actually talk to these people and find out the things which were never told to the court, which the police presumably didn't bother to ask for or were not interested in at a certain point. At the point where they had something like this, they had 2 insulin cases and they had a green post-it note, they were ready to go, and they never turned back, never stopped and thought, as far as we know. So I'm not going to dispute that, but I'm going to dispute the statistical modeling which John does, and I spent a lot of time trying to figure out what he'd exactly done, because he has a lot of words but no formulas here. I mean, it's a paper written for medics and lawyers, so I can understand that he doesn't go into the technical details of what exactly he did. This is what the chart looked like when you leave out the events which Rose and Elston think should not... the events exist, but Lucy wasn't there, so there are 10 white... there are 10 white... I mean, there's some Tipex has been put a white blob of Tipex has been put on 10 of these, of what were 10 black diamonds there. What else do we have here? Well, we have some more graphs, but this is what he's going to analyze, and I'm going to look at that analysis. And there are a couple of graphs and a histogram which tell us something about what was going on. So I've been trying to reconstruct this graph and this number and this graph from the data, and trying to follow the recipe which he himself describes here, and I simply have not succeeded, and I will show where it goes wrong. And in retrospect, one could have expected this. One could have expected something. There's a wrong idea in the theoretical model which he's using. So what is this theoretical model? It's called the beta binomial distribution, which of course sounds very fancy. A beta distribution is a probability distribution. Well, I can sort of, this might be a beta distribution. This particular curve is something else, but it's a probability distribution between 0 and 1, and it has a peak somewhere, and then it falls off. Could fall off very sharply, or it could be very broad, but it basically is spread all the way from 0 to 1, but it can get basically at 0 quite fast. And what does it stand for? The beta distribution stands for, it stands for the distribution of the relative frequencies with which each nurse is present. So it's a probability distribution over the nurses, of the nurses. And each nurse is supposed to have their own probability of being present at any of these events. So as you go down here, and you carry on down to 61, you think of the 61 all being in random order. So you just go down a much longer table like this. You go down 61 rows, and for each nurse, each nurse has their own probability to be there. So they happen to be there then, and 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 so that would go on. So that would go on 61 times, each nurse with their own probability. And we can see already some of the nurses, that probability is probably quite big, because some nurses are present 7 or 8 times. Many nurses are only there 1 or 2 times, so that, like this one and this one, they must have very small probabilities of being on duty. It kind of stands for the relative frequency over a long period that they are working a shift, over all the shifts of a long period. And we have a sample of shifts, 61 shifts, and we have a sample of 38 nurses. And if there were 38 different nurses, there would be the 38 different probabilities, but it would look all much the same. Okay, now let me go to some graphs and statistics. So here is the part of the table which he's analyzing, and I've exchanged the rows and columns, which is going to get me confused a few times, and you too probably. There are 25 events here, and there are 37 nurses because I've omitted L3. L1, L2 and L3 are the 3 nurses whose surname begins with L, and Lucy's the 3rd one, and I've left her out. I'm using the rest of the table, and this is the rest of the table. This is the table minus Lucy Letby's column, but it's on its side. Don't worry about that. Don't take any notes of that. Here are the nurse totals. So each nurse appears a number of times. A1 appears once, A2 appears once, A3 appears twice. Here are L1 and L2. L3 I've left out. Right, she was present 25 times. then there's M1, 7, M2, 7, M3, 2, and so on. Now, the idea of John O'Quigley is that if you pick for each nurse a probability, a number between 0 and 1, from a distribution looking like this, so like around 0.16, and then on the small side dropping to 0 very fast, on the other side not dropping quite so fast, but dropping fast and getting close to 0 and staying close to 0 for like half of the range from 0.16 up to 1. There should not be much probability of having, there should not be a large probability of a nurse working 50% of the time. Okay, so it's a distribution like this. You pick a nurse, you pick a nurse, create a random nurse, which means picking a probability from this distribution, and then just go down the 61 rows, tossing a coin with that probability of heads in order to fill in black diamonds occasionally for that particular nurse. And each nurse has their own probability, and so there are two sources of variation. The nurses are different, and then whether or not they're actually on duty at any moment is random as well. Per nurse, it's the same probability going all the way down 61 times. For different nurses, different ones. That's a pretty picture, and what he wants to show is that if you would do that, so first of all, he fits this distribution to the data we have, which is this, and you don't need to know how he does that. He fits this probability model to that data, and then he asks the question, suppose we made 61 shifts with 38 random nurses, what's the probability that there would be a nurse with 25 or more events in their 61? And for the model which he claims he found, that turns out to be about 50-50. So with the model which he has estimated, with the parameters, which particular one of these distributions, it turns out that in 61 shifts, you're as likely as not to have a nurse with 25, who's there 25 times. Now, so that you have like 61 candidate suspicious events. You have one nurse who's there 25 times, say, or 26, or maybe just 24, but there will be there will very likely be one nurse with markedly more than anybody else. See that nurse as a suspicious person, use the suspicion of that person to make those events where she's there, say 25 of them, suspicious events, leave out the rest of the events, so go from 61 back to 25, and you'll get, lo and behold, a table like the famous one with L3. I mean, with L3, but it would be like a different random nurse who completely by chance would be the full guy, the full gal. Now there's a problem with that, and I'm going to show you what the problem is, because the problem is that that model does not actually fit to this data. And let's look at some more numbers first. Okay, so here, these are the numbers I'm going to fit to this beta binomial distribution, and you don't have to know how I do that. I'll say some more about it, but you see these numbers here, and I'll show you some what do you call it, summary statistics of these numbers, like the mean and the variance. They're going to be interesting. The mean is about 4. The average of these numbers is 3.8. And 3.8 out of 25 is roughly 1/6. So overall, there's a nurse present in the chart 1/6 of the time of the chart, that is totality. Okay. There are the nurse totals. There I'm going to investigate them. I'm going to model them. Yeah, fancy word going to do some fancy things with them, but I think it went wrong. Here are the other totals. When you look, here are 25 row sums, and you've seen some big ones and some small ones, and not so much in between. And actually, that's largely to do with night and day. And if you look at these numbers, and especially when you correlate them with night or day, you'll see that in the daytime there's about 10 nurses present, and at nighttime there's only about 5 or 6. And you will now start to realize that a ward like this can't have much more than 10 or 11 nurses during the daytime, because it's just too small for more to fit in. And it's not, even if it's full with babies, you can't operate with that number of people in that confined space. So there cannot be large numbers of nurses, larger than 10 or something, larger than 11 during the daytime. Simply physically, that's not going to be. And at night, there's also going to be a small number. You need to have 5 or 6, and that's what you're going to have every time. And what does this mean? This means that when one nurse is present on a shift, it makes it less likely that any of the other 38 nurses are there too. The nurses, as it were, repulse one another. I think of physical models of particles repulsing one another. There's roughly a constant number of nurses every shift, different for day and different for night. And that means that this pattern which we see, this pattern, is actually much more regular than John's model suggests. And okay, here's the mean of the nurse totals. It's about 4, as I said. The variance is about the same. And notice the variance is not bigger than the mean. It's actually slightly smaller. And this, whereas his model suggests what is called fancy word over-dispersion, his model suggests that nurses are more variable than what these numbers suggest. The variance should, in fact, be bigger than the mean, somewhat bigger, and I can will show that to you in a moment. Now, the numbers published in this paper, I can't reconstruct them, but there was a draft of the same paper published a year before, or put on the website a year before, and it actually had the numbers which he was then using, which are called alpha and beta, for this beta binomial distribution. And I'm not going to explain what alpha and beta mean, but this is to do with no, I'm not going to. But I can simply pull out. There's a formula. I mean, it's implemented by a computer program. This is 1 minus the probability with this alpha and beta that in 61 shifts there would be less than or equal to 24 events. So 1 minus this probability is the probability that in 61 shifts a random nurse would have 25 or more, and it's a small probability. It's 0.013, and I think we've seen that probability in his paper. And that's a rather small probability, so this does not sound good for Lucy. I mean, we're surely not saying that Lucy has only a probability of 0.0133 of having 25 or more events in 61 shifts, which is sort of what is needed to make his story work. But the thing is, the idea is that Lucy is the most unlucky nurse. She's the nurse with probably with the biggest probability of being present. And anyway, we're looking at 38 nurses. We're looking at 38 nurses, and here I have 38 nurses, and here is the probability that, according to his model, that there would be one or more nurse out of 61 who would be present 25 times or more in 61 sort of candidate suspicious events, and it's about 40%. it's about 40%. So that means it's basically as likely or not that there would be a nurse with 25 present 25 times. Okay, and if there isn't one who's there 25 times, there's probably one who's there 24 or 23 times. So actually there is, in 61 shifts, 61 candidate suspicious shifts, you will find a nurse among the 38 who has the nurse with the largest number of presences will have enough to build exactly that incriminating spreadsheet from her. So that's the story, and that's correct. It's correct for these particular parameters which he published. Now the problem is there are a number of problems, and I will illustrate them here. Here is a histogram of the number of nurses, excluding Lucy Letby, on duty in each of 25 shifts. And so, for instance, there are 0 other nurses. The height of the bar here is 0. There are no nurses who are never there with Lucy, right? And there are 3 nurses who are each there just once with Lucy. So these are 3 nurses who each are sometime or other alone with Lucy. I think I said that correctly now. And notice this high bit here and then a dip and then big again. This looks to me like the distance between night and day again, but it's and it is definitely correlated with that. It is partly to do with night and day. This is the reality. This is the truth. Now, this is what you would expect with John O'Quigley's model. You would expect there to have been no other nurses with Lucy a couple of times, on average a bit more than 2 times. Nearly 3 times. But you also see, with fairly small probabilities, but quite a lot of them adding up over here, numbers of nurses present with Lucy much bigger than the biggest number. The biggest number was 10, right? I think, nurses with Lucy on a shift. But here we have a decent, some probability of 11 and 12 and 13 and 14 and so on. And you can really see the difference here. The red distribution is not a good estimate of the blue distribution. The model is rejected. And here's some other little calculations. If I sample 38 random nurses from this beta distribution, the biggest one is only going to be there 30% of the time. The biggest one is going to be there 30% of the time. The average is 14% of the time. So the biggest, most present nurse is there twice as often as, say, a modal nurse or a mean nurse. And we know that Lucy was 30% more often present than the mean nurse, or the modal nurse, or the nurse who was working most full-time, but not doing lots and lots of extra shifts. Lucy is somewhere between these 2 numbers. Lucy is not a random sample from this distribution at all. And here's another clue. Here I simulate 25 events, 38 nurses, 38 random nurses, and I fill them in with I give the nurses these random probabilities to be present, and then I fill in the presences according to those probabilities, each nurse independently, and then I look at the first. I look at the 25. I only did 25 events, and the mean number of presences is 3.5, which is close to 4, right? Same as last time. The variance is twice as big. Here we have in clear overdispersion. This model makes the nurses much more different from one another than they are in reality. I think that's really all I want to say here. So yeah, I should go back to, okay, so what's going on then? This model is not correct. What's a good model? It's difficult to make a good model because nurses may have independent preferences and tend to be on duty more or less often. But nurses' presences are not independent because the row totals, the number of nurses on shift, is basically close to fixed. It's like 5 in the night and 10 in the day, plus or minus 1 or 2. And if a couple of nurses are present, then it's very likely that for the other nurses, for any other nurse, that they're not there because they, as I was saying, they repel one another. This table, the zeros and ones, are much more uniformly spread out than you would expect if they were thrown there by chance. They're not random. They are more spread out. And of course, they are differently spread out in the days and the nights. So if I would look at the night part and the day part, we would see a clearly different picture with less ones in the night than in the day, obviously. But the scattering of zeros and ones for each of the two parts would be almost uniform. It would be less random than random, if you see what I mean. Right, what we do know is that Lucy does lots of extra shifts, many more than any other nurse as far as we know. We don't have the total number of shifts worked for 1.5 years by every single one of those 38 nurses, and that was like the first thing which the police should have got hold of, and was probably one of the first things that Jane Hutton told them she would need. We need so much more data to do anything, to say anything whatever about a correlation between Lucy's presence and events. And remember, correlation is not causation. Now, I believe Lucy tends to do extra shifts when the unit is packed full to the rafters of extra sick babies who should not have been there. Those are the times when babies die more frequently, where deaths happen one after the other rapidly. And Lucy is doing her extra shifts on during those periods. So it's not the deaths which follow Lucy, it's Lucy who follows the shifts. There is a correlation. Regarding the deaths, there's a correlation. It's definitely there. It's a rather strong correlation. But it's not deaths which follow Lucy. It's Lucy who is doing extra shifts when deaths are more likely. And if only we had data about acuity of all the babies, we would be able to verify this hypothesis. We can test this hypothesis. So if somebody doesn't believe me, they just need to get the data from the hospital or the police or whoever. It should be there. And I can certainly advise them what calculations to do, but I don't need to do them myself. They can hire an independent statistician to do the calculations, find out if I'm right or wrong. I don't see another explanation, because we know nobody ever saw her doing anything. And there were so many nurses on duty all the time. And nobody ever saw Lucy do anything whatsoever, anything wrong whatsoever. And police searched and searched for years looking for evidence of harm done to a baby, any baby, and they basically didn't find any. Of course, they only worked with Dowie Evans, and he found them all the time. He was very good at finding them. But when serious doctors have looked at those babies, everyone again and again, there are perfectly plausible natural reasons for death or collapse or whatever, and there's no need to hypothesize a killer. the ward was the killer, and possibly the consultants to some extent. The ward was certainly a killer ward. Lucy wasn't. Do I need to say anything else? I think I will leave it there to find out how long this one took. Stop recording.